Mother Nature often expresses herself through stunning visuals and incredible vibrations. Symmetrical forms, fractal patterns, Fibonacci spirals, and golden ratio designs are majestic representations of complex mathematical models. It is this aesthetic beauty and artistic experience in mathematics that commanded Paul Dirac to quote, "If there is a God, he is a great mathematician." Visual representations are equally important in our day-to-day life. Resource optimizations, projectile trajectories, data representations, to name but a few. Visuals empower our imagination and make things easier and fun. And one such visual representation in mathematics is the graph of a function. It is a quick and reliable representation of the relationship between the variables, which helps us analyze the behavior of a function as a whole as well as at specific points. From a mere glance on the graph, we can find out if at all it represents a function and can also find its domain and range. Within a fraction of seconds, we can identify if it is one or many one, into or onto, periodic or non-periodic. For a bijective function, we can quickly draw the graph of its inverse function. Limits, continuity, differentiability, monotonicity, concativity, critical points, points of local maxima, points of local minima, and points of inflection all can be worked out in a jiffy. Graphs help find definite integral value for some functions and are fundamental to calculate the area under the curve. From graphs, not only we can solve equations but also inequalities. Most of us often unknowingly appreciate the beauty of mathematics in nature, but it entails the selected few to understand it as well. We'll first start with representation of function. So a function is generally represented as f from a to b, y equals fx. So this function f, it defines the relationship between two variables x and y, and it is defined from the set A, which is also called as its domain, to its set B, which is called as its codomain. The first thing that we can decide from the graph is whether the given graph represents a function or it is just a relation, and for that we'll use something called as vertical line test. So I'll take up an example. So suppose I have this graph, and this graph is defined from R to R, and I need to know whether this graph represents a function or it is just a relation. I'll draw a vertical line and I'll mark its point of intersection. Now I'll move this line along the domain of the given function. So there are two conditions. First condition is, for each and every point, there must exist an image. So that means if I'm going to move this line in its domain, so I must always get a point of intersection. So if there is any point in the domain where I don't get this point of intersection or where there is no graph, so then it is not a function. Now the second condition is the image of an element must be unique. So that means if I'm going to draw a line at any point, there must only be one point of intersection. If I get more than one point of intersection, then it is not a function. Then it is just a relation. Now for this one, I know every time if I'll draw a line, there'll be a point of intersection and there'll be only one point of intersection. So that means this graph represents a function. Now what about this one? So if I draw a vertical line, I get 2 points of intersection. So that means it is not a function. It is just a relation. Now the second thing that we'll decide from the graph is domain of a function. Now domain is the set of values of x that a function can take. So if I have to find domain of a function, I'll need to identify the region where the graph exists. Say for example, suppose I have this graph. Now for this function, the graph is defined between x equals to -2 and then x equals to +2. Now when x is less than -2 or when x is greater than +2, there is no graph. So that means if I have to write the domain of this function, I'll simply say the domain of this function is x belongs to from -2 to +2. Now what about this one? Now for this function, I have this graph at all points except at -1 and at +1. So that means the domain of this function is x is unequal to plus or -1, or in other words, I can write x belongs to r minus -1 and +1. So the third thing that I can find out from the given graph is its range. So basically range is the set of values of y. So if I have to find the range of function, I need to know what are the values of y that this function can take. So I'll start with this question itself. So this function, it takes all the values of y between 0 and 1. So that means the range of this function is y belongs to included 0 to included 1. Now, what about this second one? Now it starts from minus infinite and then it goes all the way up to 0. Now there is no graph between 0 to 2, and then from y equals to 2 to y equals to infinite, again the graph exists. So in this case, y can take all the values from minus infinite to 0 and then from 2 to infinite. So I'll simply write the range of this function is y belongs to, so from minus infinite to 0. Now, should I include 0? I cannot include 0 because, so the graph approaches 0, but then it won't actually take this value 0. So that's why I'll write this 0 in open interval and then union. So now there are no values between 0 and 2 from 2 to infinite. So range of this function will be from minus infinite to 0 union 2 to infinite. So what about this one? Now, when I look at this function, this entire graph lies between this line and y equals to 1. So basically, it takes all the values between 0 and 1. So range of this function is y belongs to 0 to 1. Now, it's actually taking the value 0 at both plus and minus log 2. So I'll include 0. And it's also taking the value 1 at 0. So range of this function will be from 0 to 1, both included. Now, the fourth thing that we can decide from the given graph is whether the given function is a one-one function or a many-one function. And one-one functions are also called as injective functions. So I can decide whether the given function is injective or not injective. Now, for this, we'll use something called as horizontal line test. So I'll take up an example. Say, for example, in order to decide whether the function is one-one or many-one, I'll draw a horizontal line and I'll mark its point of intersections. Now I'll move this line up and down. So if every time I'm getting only one point of intersection, so that means for one value of y, I'm getting only one value of x. In that case, function will be a one-one function. If I'm getting more than one points of intersection, then the function will be many-one function. Now in this case, when I draw a horizontal line, I'm getting 2 points of intersection. So that means this function is a many-one function. Now the same function can be one-one and many-one depending on its domain. Now say for example, if I define this function f from R to R, now here I'm getting more than one point of intersection. So this function will be a many-one function. But what if I restrict the domain? Suppose I define this function from 0 to infinite to R. Now in this case, when the function is defined from only 0 to infinite, then if every time I'm going to draw a line, I'll only get 1 point of intersection. So in the restricted domain of 0 to infinite, this function will be a one-one function. So when we are deciding whether the function is one-one or many-one, then in that case, we must take care of its domain also. Now, what about this one? Is this one-one or is it many-one function? So now if it is defined from minus infinite to plus infinite, if I draw a line, so I'm getting more than 1 point of intersection. So this again is a many-one function. Whether the graph is an into function or an onto function, and onto functions are also called as surjective functions. Now this one is pretty simple. You'll be given a function which is defined from a to b. Now find the range of this function. So we have already studied how to find range from the graph. Now compare this range with the codomain. If the range is equal to codomain, then the function is an onto function. If range is unequal to codomain, or if range is a subset of codomain, then basically it is an into function. If range is a superset of codomain, then it is not a function. Now say for example, so I need to say whether this function is into function or an onto function. So basically this graph, it takes up all the values from minus infinite to plus infinite. So range of this function is y belongs to R, all real numbers. Now I look at its codomain. Its codomain is also R. Now in this case, range and codomain, they are equal. So when range and codomain, they are equal, this function is an onto function. Now, can you tell me whether this function is 1, 1 or many 1? So I'll draw a line. I'll draw a horizontal line. I get more than one point of intersection. So it is many 1 function. So this function is many 1 and on 2. Now let us take another example. Say for example, I'm given a graph. Now this function is defined from r minus 0 to r, and we need to find out whether this function is 1, 1 or many 1, and this function is into or onto. Now for 1, 1, I'll draw a horizontal line. So when I draw a horizontal line, I'm getting only one point of intersection every time. So this function is actually a 1, 1 function. Now what about range of this function? The range of this function will be y belongs to r minus 1. So range is r minus 1, codomain is r. Now here the range is not equal to codomain. Now when range is not equal to codomain, it is an into function. So this function is 1, 1 and into. Now the sixth thing that we'll decide from the graph is whether the function is a bijective function. Or in other words, we'll say whether the function is invertible. So if a function is both injective as well as surjective, then we'll say a function is bijective. And when a function is bijective, only then its inverse exists. Suppose the function is defined f from r to r, and I need to know whether inverse of this function exists or it doesn't exist. So first I'll check whether this is 1, 1 function or many 1 function. So I'll draw a horizontal line. So when I'll draw a horizontal line, I see 3 points of intersection. So basically it's a many 1 function. Now when it's a many 1 function, it cannot be a bijective function. Now what about this one? So when I draw a horizontal line, I get only one point of intersection. So that means this function is a 1, 1 function. Now what about range? So range is from 0 to infinite, and codomain is also from 0 to infinite. So when range and codomain they are equal, this function is an onto function. So now when a function is both 1, 1 and onto, it's a bijective function. Now the seventh thing that we can do is, if we know a function is invertible, we can draw the graph of its inverse function. So suppose I have a function which is defined from a to b, y equals fx, and suppose this function is a bijective function, then its inverse function f inverse will be defined from b to a. So its inverse function will be defined from b to a, and it will be defined as y equals f inverse of x. Now how do we draw the graph of inverse function? Now there are two methods. Now method one is by taking the reflection about y equals to x line. Say for example, a function is defined from r to r, and this function is defined as y equals x cube. So I'll draw the graph of y equals to x cube. So first I'll draw horizontal lines. So I'm getting only one point of intersection. So this function is a 1, 1 function. And what is the range of this function? So it takes all the values from minus infinite to plus infinite. So its range is y belongs to r. Now range and codomain, they are equal. So this function is both 1, 1 and on. Now that means inverse of this function exists. Now inverse of this function will be defined from r to r. So f inverse will be defined from again r to r. And in order to write its inverse function, what I'll do is I interchange x and y. So I'll write x equals y cube, or I can simply write y is x to the power 1 by 3. So inverse of the function y is equal to x cube is y equals x to the power 1 by 3. Now we'll draw the graph of cube root of x. So one way of doing it can be, so on the graph of y is equal to x cube, I'll draw this y is equal to x line, and then take the reflection of the graph of fx about y equals to x line. So if I take the reflection of this graph, so I can draw this graph as, so this is the graph of y equals x to the power 1 by 3. I'll take up another example. Now suppose I have this function. Now this function f is defined from 0 to pi to minus 1 to plus 1, and the function is y equals to cos x. Cos 0 is 1, cos 90 is 0, and then cos pi is -1. Between 0 to pi, if I draw horizontal lines, I'll get only one point of intersection. So that means this function is a 1 function. Now, what about range of this function? So minimum value of this function is -1 and the maximum value of this function is +1, and it takes all the values between -1 and +1. So that means range of this function is y belongs to -1 to +1. And its codomain is also from -1 to +1. So when range and codomain they are equal, function is an onto function. So this function is both 1, 1 and onto. And when a function is both 1, 1 and onto, it's a bijective function. Now I'll need to find the inverse of this function. Now because f is defined from 0 to pi to -1 to 1, f inverse will be defined from -1 to 1 to 0 to pi. And I'll write the inverse function. So I'll interchange x and y. So if I'll interchange x and y, I'll get what? I'll get x equals cos y. Now if I can find y, so I can write y as y equals to cos inverse of x. So I'll need to draw the graph of y equals cos inverse of x. So how do I draw this graph? So one of the way of doing it can be, I can draw y is equal to x line. Then I can take the reflection of this graph about y is equal to x line. Another way of drawing the graph of cos inverse x can be, now I know the domain of this function is from -1 to +1. So I'll mark -1 and then +1. And I'll also mark the values of y. So in order to draw this graph, I'll take up a point on this function fx, and then I'll interchange the values of x and y, and I'll mark that point on the graph of inverse function. So what about this point? So this point is expressed as 0, 1. So that is when x is 0, y is 1. If I'll interchange x and y, now I'll get 1, 0. So I'll mark this point. So this point is 1, 0. Now I'll come to this point, pi by 2, 0. So I'll interchange x and y. Now I'll get 0, pi by 2. So when x is 0, y is pi by 2. Now finally I'll come to this point. So this point is pi, -1. So when x is pi, y is -1. So if I'll interchange, so when x is -1, y is pi. Now I'll draw an approximate graph. So an approximate graph will actually look like this. So that is the graph of cos inverse x. Now we'll come to the eighth thing. Now eighth thing that we'll decide from the graph is whether the function is a periodic function or it is a non-periodic function. If my graph has some pattern which repeats after a certain interval every time, then I'll say my function is a periodic function. Now say for example graph of y equals to sin x. Now when I look at the graph of sin x, I see this pattern. Now this pattern, it gets repeated every time. So it is a periodic function, and the length of this interval is called as fundamental period of that function. So in the case of sin x, the fundamental period is 2 pi. Now the ninth thing that we'll decide in a graph is whether the function is a continuous function or a discontinuous function. So if the graph of function is connected, then we'll say the function is continuous. And if the graph of function is disconnected at any point, then we'll say this function is discontinuous at that point. So in order to decide whether the function is continuous or discontinuous, all you need to do is you need to draw the graph. And if while drawing the graph, my pen lifts, then the function is discontinuous at that point. And if I don't need to lift my pen, then the function is continuous. Say for example, now this function f is defined from R to R. Now I need to know whether this function is a continuous function or a discontinuous function. So if I'll try to draw this graph again, I don't need to lift my pen, right? So that means I'll say this function is continuous for all real numbers. So this is continuous in all x belongs to R. Now what about this one? Now if I'll try and draw this graph, my pen, it is going to lift at x equals to 0. And if I'll draw it again, now again my pen is going to lift at x equals to 4. So that means this function is discontinuous at x equal to 0 and x equal to 4. Now the 10th thing that we'll decide in a graph is its differentiability. Whether a function is differentiable or not differentiable. Now for differentiability, there are two steps. Now step number 1, discontinuity implies non-differentiability. If function is discontinuous at some point, I'll straight away say this function is also not differentiable at that point. Now, second thing is, what if a function is continuous at a point? If function is continuous at a point, I'll need to check its differentiability. If at any point the function changes smoothly, then the function is differentiable at that point. Now, if a function has sharp corners or a cusp or a point where it has a vertical tangent, then so at that point the function will be continuous, but it won't be differentiable. So in differentiability, what exactly we are looking for? At any point, say at x equals to a, if I'm to approach this function from the left hand side and I draw a tangent, and if I draw the tangent on the right hand side, and again if I approach this point, if I get both the tangents same, then I'll say the function is differentiable. If I have a point where left hand tangent is different than a right hand tangent, then I'll say this function is not differentiable. Now in this case also, so now this is tangent on the left and this is tangent on the right. So this again is not differentiable. Now at this point, I get a vertical tangent, and vertical tangent slope is infinite. So then again, this function is not differentiable. Say for example, so suppose this is the graph which is given to me. Now when I look at this graph, I know if I'll draw this graph, my pen is going to lift at 0. So it is discontinuous at x equal to 0. So this function is discontinuous at x equal to 0, but at all of the points, this function is continuous. So there is only one point where this function is discontinuous. Now, when we talk about differentiability, clearly I know because at 0, this function is discontinuous. It is not differentiable at x equal to 0. Now I see an edge at -2 and +2. So because I see two different tangents at -2 and +2, this function will also not be differentiable at x equals to -2 and x equals to +2. So this function is discontinuous at x equals to 0, and this function is not differentiable at x equals to 0, x equals to +2, and x equals to -2. Now I'll take up another example. Now what about differentiability of this function? So I can draw this graph without actually having to lift the pen. So that means I can say this function is continuous for all x belongs to R, but it is not differentiable at x equals -1, 0, and +1. So we can decide continuity and differentiability from the given function. Now the 11th thing that we can decide from the given graph is its interval of monotonicity. I can find the interval where this function is increasing, and I can also find the interval where this function is decreasing. So if the value of function increases, I'll say it is an increasing interval, and if the value of the function decreases, I'll say it's a decreasing interval. I'm given this function. And when I look at this function increases for all the values, right? So as the value of x increases, the value of y also increases. So I'll say it is increasing in x belongs to R. Now what about this one? Now this function is first increasing from -infinite to 0, and then it decreases from 0 to infinite. So that means from -infinite to 0, this function is an increasing. From 0 to infinite, this function is a decreasing function. Now the 12th thing that we can decide from a graph is its critical points, and also from these critical points, we can say whether it is a point of minima or a point of maxima. Now there are two kinds of critical points. So first, all the points where the function is not differentiable, and secondly, points where I have a horizontal tangent, that is the points where derivative is 0. Say for example, so this function is not differentiable at x equals to -2, x equals to 0, and x equals to 1. So these are my first set of critical points. Now I'll also need to find the points where I may have a horizontal tangent. So if I look at this point, maybe I'll say this point is -1. So at this point, if I'll draw a tangent, this tangent will be horizontal. So I'll get another critical point and there will be x equals to -1. So this function, it has 4 critical points, -2, 0, 1 and -1. Now, how do we know if a point is point of local maxima or local minima? Now look at the value of this function at x equals to a. Now on the left hand side of a, I look at the graph. So this graph on the left hand side of a lies below the value at a. Now on the right also, the graph lies below the value at x equals to a. So that means if at a the value is greater from its left hand neighbor and its right hand neighbor, then I'll say this function has a local maxima at x equals to a. In the same way, if at x equals to a, suppose I have this value at x equals to a, fx. Suppose at a I have this value which is fa. Now just before a, the graph lies above this line, and after a also the graph lies above this line. So if the value is less than both its neighbor, then I'll say it's a point of local minimum. Now what about x equals to -2? What's the value at -2? So the value at -2 is 0. Now just before -2, the graph is above this line. Now right after -2, the graph is, so that means at -2, it is neither maxima nor minima. Now what about -1? So at -1, I have this value which is represented by this line. Now just before -1, graph lies above, and right after -1, the graph again lies above. So that means at -1, it is local minima. So -1 is a point of local minima. So this function has 4 critical points, -2, 0, 1 and -1. And of these 4 points, it has local minima at -1 and +1. And at -2 and 0, it is neither local maxima nor local minima. Now the 13th thing that we'll study in a graph is its concavity and to know whether any function has a point of inflection. So there are 2 kinds of graph. The graph which are concave up and the graph which are concave down. So basically we can determine concavity by second derivative, d2y upon dx square. If second derivative is positive, it is concave up, and if second derivative is negative, then it is concave down. At point of inflection, the concavity of graph changes. I'll draw a graph. Now before x equals to 0, this graph is concave up, and after x equals to 0, this graph is concave down. So that means this point x equals to 0 is point of inflection. Now I take another one. Now in this case, when x is less than 0, the graph is concave down, and when x is greater than 0, graph is concave up. So that means again the concavity changes at 0. So at x equal to 0, this again is point of inflection. Now at 0, when I look at the value at 0, so value at 0 is 0. Now the graph right before 0 is above this line, and the graph right after 0 is above this line again. So 0 is also point of local minima. So it's a point of local minima and it is a point of inflection. For some functions, we can find the value of definite integral using graphs. So it may not necessarily be true for each and every function, but then for certain functions, we can definitely calculate the value of definite integral. Say for example, this box x represents greatest integer function. So we'll actually draw this graph when we'll study its transformation, but right now I'll just draw the graph. So at this point, don't bother about from where this graph has come. So the graph which I have drawn in green is actually the graph of this function of y equals 2 upon e to the power x. Now, if you have studied definite integral, then definite integral is the area of the graph with x-axis with plus or minus sign. If the graph lies above x-axis, we'll take a plus sign, and if the graph lies below x-axis, we'll take a minus sign. So now in this case, the only area which is possible is this rectangle which is between 0 and log 2. So the value of this definite integral is log 2. I'll take another example also. Say for example, so suppose I have this function y is equal to fx, and I need to find the integral of this function from 0 to 3 fx dx. Now again, when I look at this function, I see this rectangle and I see this small triangle. So the value of this definite integral is 2 minus 1 by 2, which is 3 by 2. Now the 15th reason why we should study graphs is area under the curves. Now area under the curves is one such topic which will require the extensive use of graph. So whether if I have to find area bounded by the curve and x-axis, or area bounded by the curve and y-axis, or area bounded by multiple curves and x-axis, or area bounded by two given curves, I'll need to draw the graph before I can start solving the problem. So as of now, I won't get into integration, so I'll take a very simple example. I'll need to find the area of this function between x equal to 0 and x equal to 4 with x-axis. So the area of this function will be, so what is the area of this rectangle? Area of this rectangle is 2 plus, what is the area of this triangle? Area of this triangle is 1 by 2, and then plus, what is the area of this triangle? Area of this triangle is again 1 by 2. Now in case of area, we don't take negative values. We'll just add all the areas, right? So this again, I'll take it as 1 by 2. So the area under the curve for this function will be 3 square unit. Now the 16th application of graphs is perhaps one of the most interesting and fascinating applications of graph. So we can use graph to find number of solutions of an equation. Now suppose I have this question where it says fx equals gx, and I need to find number of solutions to this equation. So if I have to just find number of solutions of this equation, what I can do is I can draw the graph of y equals to fx, and then I'll also draw the graph of y equals to gx. Now I need to find all those points where the value of fx is equal to value of gx. So what I'll do is mark all the points of intersection. So therefore the number of solutions to this equation is equal to number of points of intersection of these two graphs. So in this case, the number of solution of this equation will be 4. So if we have to find number of solutions of any equation, then we can simply draw the two graphs and we can find their points of intersections. Say for example, cos x equals x square. So if I'll draw the graph of cos x, I will go on, and if I'll draw the graph of x square, so now these two graphs, they have 2 points of intersection. So number of solutions of this graph will be 2. Now the 17th application of graph is solution of inequalities. So suppose I have any inequality which says fx is greater than gx. Now one way of doing it can be, I can draw the graph of fx, I can draw the graph of gx. Now in order to solve this inequality, first thing that I'll do is I'll find their point of intersections. So I'll solve this equation fx equals to gx, and I'll find their point of intersection. Suppose x equals to a, x equals to b, and this is x equals to c. Now I need to solve this inequality. So I need to find the interval where fx is greater than gx, or the interval where the graph of fx lies above the graph of gx. Now the graph of fx, it lies above the graph of gx in this interval and in this interval. Now also it doesn't have an equality sign, so I'll use open circles. So answer to this inequality will be x belongs to, so from minus infinite to a union b to c. Now say for example, sin x is less than equal to cos x between 0 to pi. So between 0 to pi, this is the graph of sin x, and I'll draw the graph of cos x also. So that is the graph of cos x, and the point of intersection is pi by 4. So blue graph, it's a graph of cos x, and this red graph, this is the graph of y equals to sin x. Now I need to find the interval where the graph of sin x lies below the graph of cos x. So the graph of sin x lies below the graph of cos x in this interval, and because it has an equality sign, so I'll include it. So in this interval from 0 to pi by 4, graph of sin x is actually less than graph of cos x, but from pi by 4 to pi, the graph of sin x is greater than graph of cos x. So answer to this inequality will be x belongs to from 0 to pi by 4, 0 included, and pi by 4 also included. Now these 17 cases clearly illustrate how imperative it is for us to study graphs. Now there are many more applications of graphs, but then as of now we'll restrict to these 17 cases, and if need be, I'll add more cases as and when it is required. Thank you. Now in this lecture we'll study some basic graphs. So after this chapter we'll be studying transformation of graphs. So in order to make complicated graphs or smart graphs, we must know the basic graphs. So I'll start with the first graph itself, and the first graph is the graph of a constant function. Say for example, a function is defined as fx equals c. So in this case, I'll just need to draw a line parallel to x-axis at the point y equals c. Say for example, the graph of y equals minus 3 by 2. So I'll draw the axis, and then at minus 3 by 2, I will draw straight lines. So this is the graph of a constant function. The second function is identity function. Now identity function is defined as fx is equal to x. So it's a straight line and inclined at an angle of 45 degrees. So this is the graph of y squared to x line, which is an identity function. Now the third graph that we'll study is modulus function. Now modulus function is expressed as fx equals mod of x, and we know that mod of x is actually minus x when x is less than 0, and then plus x when x is greater than or equal to 0. So if I have to draw this graph, I'll draw the axis, and when x is greater than 0, it is y is equal to x line, and when x is less than 0, it is y is equal to minus x line. So that is the graph of mod x. So it's a V-shaped graph. Now fourth function is signum function. Now basically signum function is defined as sgnx. So I'll write fx equals sgnx, or I can express it as mod x upon x when x is unequal to 0, and this is 0 when x is equal to 0. So when x is less than 0, what I know is mod x is minus x. So it will be minus 1 when x is less than 0, 0 at x equals to 0, and when x is greater than 0, mod x is basically plus x. So plus x upon x is 1. So if I have to draw this graph, then when x is less than 0, this is minus 1, 0 at x equals to 0, and when x is greater than 0, then its value is plus 1. So that is the graph of signum function. So there may be some questions where they may use signum function in composition with some other function, signum of fx. So now when I see signum of fx, what I clearly know is wherever fx is less than 0, its value should be minus 1. Where fx is equal to 0, it should be 0. And where fx is greater than 0, then this value should be plus 1. Now say for example, if I'll say find signum function of mod x. So I'll draw the graph of mod x. Now where mod x is 0, mod x is 0 at 0. So where fx is 0, signum function is also 0. Now when x is less than 0 or when x is greater than 0, here the graph of mod x lies above x-axis. That means in this case, it will be positive. So when fx is positive, then the value of signum function is +1. So that means I'll draw these lines. So the graph of signum of mod x will be this graph. Let me take another one. So suppose I need to find signum of sin x when x belongs to 0 to 2 pi. So I'll draw the graph of sin x. This is 0, pi and 2 pi. Now, wherever sin x is 0, it'll take the value 0. Wherever it is positive, it'll take the value +1. And wherever this function is negative, it'll take the value -1. So, the graph which I have drawn with black ink is the graph of signum sin x. Now, the fifth graph that we'll study is linear function. Now, basically, linear function is a straight line. Say, for example, fx is defined as ax plus b. Now, how do we draw a line? So, there are two ways. Either I can use y equals to mx plus c, so a is slope and b is intercept. Or we can always take up 2 points, and then by connecting these 2 points, we can draw a straight line. Say, for example, function fx is defined as 2 minus 3x. Now, when x is 0, y is 2, and when y is 0, x is 2 by 3. So, if I'll connect these 2 points, I'll get this straight line. So, this is the graph of fx equals 2 minus 3x. So, any linear function is nothing but a straight line. Now, the sixth function that we'll study is graph of quadratic expressions. So, a quadratic expression is given by ax square plus bx plus c. Now, depending on the sign of this a, this graph is going to represent a parabola, either opening upwards or parabola opening downwards. So, if a is greater than 0, then it is parabola opening upwards, and if a is less than 0, then it is parabola opening downwards. Now, in both the cases, this point is called as vertex of parabola. Now, vertex is given by minus b upon 2a and minus d upon 4a. Here also it is given by minus b upon 2a and minus d upon 4a. Another way to find vertex is by differentiating the function. So, when a is greater than 0, it is parabola opening upwards, and when a is less than 0, it is parabola opening downwards. So, we'll start with the case when a is greater than 0. Now, suppose when a is greater than 0, so that means it's a parabola opening upwards. I'll take 3 separate cases. Case 1, when d is greater than 0. Case 2, when d is equal to 0. And case 3, when d is less than 0. So, if a is greater than 0, it will be parabola opening upwards, and d is greater than 0 means it will have 2 real roots. So that means this graph will intersect x-axis at 2 distinct points, and these 2 distinct points will be roots of this equation. Now when d equals to 0, this graph will just touch the x-axis, and both the roots, they'll be equal, and this is the point of contact. And when d is less than 0, then graph will open upwards, but it won't have any real roots. So that means in this case, this graph will always lie above x-axis. Now in the same way, if a is less than 0, then again we have 3 separate cases: d greater than 0, d is equal to 0, and d is less than 0. So opening downwards and 2 real roots, alpha, beta. Opening downwards, 2 equal roots, so it touches the x-axis, alpha equals beta. And then third case, where it doesn't have any real roots, so then in that case, it will always lie below x-axis. Suppose, for example, I have to draw the graph of fx equals x square minus 3x and then plus 2. So if I can factorize it, I'll factorize it. So I'll write x minus 1, x minus 2. Now it's a quadratic equation with positive leading coefficient. So a is greater than 0, so it'll open upwards. That has 2 roots, x equals to 1 and x equals to 2. So it will intersect x-axis at 1 and 2. So vertex will be given by minus b upon 2a and minus d upon 4a. So if I have to draw this graph, the roots are 1 and 2. The vertex is at 3 by 2 and minus 1 by 4. And if I'll also write value at 0, value at 0 is what? Value at 0 is 2. So this is the graph of x square minus 3x plus 2. I'll take another one. Say for example, x equals 2x minus x square. Now in this case, a is less than 0. Roots are x equals to 0 and x equals to 2. Now vertex will be 1, comma 1. So if I have to draw this graph, now roots are 0 and 2. Now at 1, value is 1. So it is parabola opening downwards. So this is the graph of y equals 2x minus x square. Now what about this one? fx is x square minus x plus 1. Now in this case, a is greater than 0. But what's the value of d? Value of d is 1 minus 4, which is minus 3. So d is less than 0. So that means it will represent a parabola opening upwards and it will not intersect x-axis. So if I have to find its vertex will be, now the value of x is 1 by 2 and 3 by 4. So if I have to draw this parabola, so then this is 0. I'll take the vertex. So this is 1 by 2 and this is 3 by 4. And what is the value at 0? Value at 0 is 1. So I'll simply draw the parabola like so. This is how we draw graph of quadratic expressions. Now, seventh graph that we'll study is graph of circles. The basic equation of circle is given as x square plus y square equals a square. So center of this circle is at origin and radius is equal to a. So if I have to draw this graph, then I'll simply draw a circle with center at 0 and radius a. So say for example, I have to draw this circle x square plus y square is equal to 4. Now center at origin and radius 2. So this is the graph of x square plus y square is equal to 4. Now what if I write this equation as y square equals 4 minus x square, or I can write y equals plus or minus under root of 4 minus x square. Suppose someone says draw the graph of this function y equals under root of 4 minus x square. Now if I'm going to square this function, I'll get the same circle, but because it's a positive sign here, so that means it will represent that part of the circle which lies above x-axis. So in this case, it will represent a semicircle. And what if I say draw the graph of y equals minus under root of 4 minus x square? So again, it will represent the same circle, but here it will represent part of the circle which is negative. So which is semicircle which lies below x-axis. The eighth graph that we'll study is graph of parabolas. Now taking a as a positive number, we have 4 different forms of parabolas. Y square is equal to 4ax, which is first form. Second form is y square is equal to minus 4ax. Third form is x square equals 4ay. And fourth form is x square equals minus 4ay. Now in the first case, it will represent a parabola opening rightwards. Now in the second case, it will represent a parabola opening leftwards. In third case, it will represent a parabola opening upwards. And in the fourth case, it will represent a parabola opening downwards. Now say for example, I have to draw the graph of y equals minus 3x square. So when I see this, so this is x square and then minus 1 upon 3y, which is fourth form. So graph of this parabola will be parabola opening downwards. Now the ninth graph that we'll study is graph of ellipse. So basically in ellipse, there are 2 standard forms. X square upon a square plus y square upon b square equals 1 and y square upon a square plus x square upon b square equals 1. So if I'll draw the graph, it'll look like So this is a comma 0 and minus a comma 0. So these are the two graph of ellipse. Now say for example, if someone says draw the graph of y equals minus of under root 4 minus 2x square. So if I'll square it, then I'll get 2x square plus y square is equal to 4. So if I'll divide it by 4, I'll get x square upon 2 plus y square upon 4 equals to 1. So basically it is second form of ellipse, and because there is a negative sign, so I'll take the part of an ellipse which lies below x-axis. Now the 10th graph is graph of hyperbola. Again for hyperbola there are two forms. So in order to draw a hyperbola, we'll first draw two lines which we call asymptotes of hyperbola. And then we'll mark these 2 points, a comma 0 minus a comma 0. We will draw the two branches of hyperbola. Similarly, for the second one, we'll mark the points on y-axis and then we'll draw two branches up and down. Now in hyperbolas, there are two more graphs, and these two graphs are graphs of rectangular hyperbolas. xy equals c square and xy equals minus c square. Now in the first case, the product of two variables is positive. So that means it will either lie in the first quadrant or it will lie in the third quadrant. So it's a hyperbola whose asymptotes are coordinate axis. And in the second case, product of xy is negative, so it means either lie in the second quadrant or it will lie in the fourth quadrant. Now say for example, if I have to draw this graph, y equals minus 6 upon x. So it means it represents a rectangular hyperbola which is xy is equal to minus c square. So I'll draw the graph in second and fourth quadrant. So that is the graph of y equals minus 6 by x. So the 11th graph that we'll study is graph of trigonometric functions. So which is graph of sine, cos, tan, secant, cosec and cot. So I'll start with the graph of sine x. So my function is y equals sine x. So this is the graph of sine x. Now suppose I have to draw the graph of y equals a sine x, and a is greater than 0. All I need to do is I'll just need to change the amplitude with this vector a. So say for example, suppose I have to draw the graph of y equals 3 sine x. So for 3 sine x, I'll just change the amplitude from minus 1 to plus 1 to minus 3 to plus 3. So if I know the graph of sine x, I can draw the graph of a sine x. Now what if I need to draw the graph of y equals sine ax? Now if I have to draw the graph of y equals sine ax, so what actually I'll do is, so first I'll draw the graph of sine x and then I'll divide every value by a. So that's the graph of y equals sine ax. Now say for example, if I have to draw the graph of y equals sine 2x. So I'll draw the graph of sine x and then I'll divide every value by 2. So basically, it's a graph of sine 2x. So next we'll take the graph of cos x. Y equals cos x. So there's the graph of y equals cos x. Now the graph of y equals to tan x. For tan x, I'll draw x-axis and I'll draw y-axis. And then I'll draw asymptotes at odd multiples of pi by 2. So I'll draw these dotted vertical lines at odd multiples of pi by 2. So now I'll draw the graph of 10x. So there is a graph of 10x. Now fourth graph that I'll draw is graph of y equals cot x. So for cot x, again I'll draw the asymptotes, and here asymptotes will be, so at n pi. So I'll draw these vertical lines at n pi. So that is the graph of cot x. Now fifth graph is graph of y equals cosec x. Now in order to draw the graph of cosec x, I'll draw a dotted graph of sin x. Now wherever sin x is 0, there cosec x won't be defined. So I'll draw vertical asymptotes at n pi. So I'll draw vertical lines at pi, 2 pi, minus pi, and minus 2 pi. Now cosec is basically nothing but the reciprocal of sin x. So what I'll do is I'll start drawing the graph of cosec x from the graph of sin x. So if it lies above x-axis, I'll draw the graph above x-axis, and if it lies below x-axis, I'll draw the graph below x-axis. So that's the graph of y equals cosec x. Then the same way I can draw the graph of secant x. So I'll draw a dotted graph of cos x. I'll draw asymptotes at odd multiples of pi by 2. And then as we did for cosec x, I'll draw the same with secant of x. So this blue graph actually represents the graph of secant of x. Now the 12th graph that we'll study is graph of exponential functions. So which is fx equals a to the power x. Now depending on this value of a, if a is greater than 1 or if a lies between 0 and 1. So if a is greater than 1, in that case exponential function is an increasing function, and when a lies between 0 and 1, then exponential function will be a decreasing function. So exponential function is always positive, so it will always lie above x-axis. If a is greater than 1, then it is an increasing function, and if a lies between 0 and 1, then it is a decreasing function. Say for example, y equals e to the power x. Now value of e is 2.7 something, so basically it is greater than 1. So I'll draw an increasing function. And what about y equals to e to the power minus x? Now e to the power minus x is basically 1 upon e to the power x. So in this case, a lies between 0 and 1. So now it will be a decreasing function. So the 13th function that we'll study here is logarithmic function. Now any logarithmic function is expressed as fx equals log x to the base a, where the value of x should be positive. Now here again, the graph of this function will depend on the base of this log. So when base is greater than 1 and when base lies between 0 and 1. So when the base is greater than 1, in that case log x is an increasing function. And when base lies between 0 and 1, then log x will be a decreasing function. Say for example, say fx equals ln x, which is log x to the base e. Now here, because base it is greater than 1, so graph of log x is an increasing function. So the 14th graph that we'll study is y equals x to the power n, where n is a natural number. Now depending on whether n is an odd number or an even number, so I'll get two separate cases. Case 1, when n is an even number, say x is 2 to the power k. And secondly, when n is odd, suppose x is to the power k plus 1. So in this case, the approximate shape of graph will be a parabola opening upwards. So say for example, if I have to draw the graph of y is equal to x square or x4 or x to the power 6, then approximately the shape of the graph will be given by this curve. So when the power of x is odd, then the graph of x to the power 2k plus 1 will be given by this curve. So if I have to draw the graph of x cube or x to the power 5, then in all such cases, basic shape will be given by the same graph. The 15th graph is graph of y equals x to the power 1 by n, where n is a natural number. Now here again, I'll take two separate cases. Case 1, when n is an even number, and case 2, when n is an odd number. So if n is an even number, I'll write y equals x to the power 1 upon 2k. Now in this case, clearly I know value of x should be 0 or greater than 0. So for this, the basic graph will be given by this curve. So say for example, if I have to write y equals to under root x or 4th root of x, so I'll use this basic shape. And when n is an odd number, so if I have to write y equals x to the power 1 upon 2k plus 1. So in this case, the basic shape is given by the given curve. Say for example, if I have to draw the graph of cube root of x or 5th root of x, so then I'll use this curve. Now the 16th graph that we'll study is graph of greatest integer function. Now greatest integer function is represented as fx equals this box x, where this box represents greatest integer. Now in greatest integer function, what we clearly know is when x lies between 0 and 1, the value of greater function of x is 0. Now when x lies between 1 and 2, its value is 1. Between 2 and 3, its value is 2. In the same way, between minus 1 and 0, value is minus 1. Between minus 2 and minus 1, value is minus 2. And between minus 3 and minus 2, value is minus 3. It is also called as a step function. So that is the graph of greatest integer function of x. Now 17th function that we'll study is graph of fractional function. A fractional function is represented by where these brackets represent fractional part of a number. Now fractional part function is actually a periodic function. So I'll draw the axis and then I'll draw these lines. So this is the graph of fraction part of x. Now the 18th graph that we'll study is graph of the functions, which is 1 upon x to the power 2n and 1 upon x to the power 2n minus 1, where n is a natural number. Now for the graph of y equals 1 upon x to the power 2n, what we clearly know is this graph won't be defined at x equals to 0. So that is the graph of any function which is of the form 1 upon x to the power 2n. Say for example, y equals 1 upon x square or 1 upon x to the power 4. In the same way, for y equals 1 upon x to the power 2n minus 1, the graph will take this form. For example, the graph 1 upon x or 1 upon x cube, they all will have the same basic shape. Now the equation which is given to us is 10x equals to x. And I have to find the smallest positive root of this equation. What I'll do is, I'll draw the graph of 10x and I'll draw the graph of y equals x line. So first I'll draw the graph of 10x. So that's the graph of 10x. Now I'll draw the graph of y equals x line. Now what I clearly know is calculus inequality says sin x is less than x is less than 10x when x belongs to 0 to pi by 2. That means the graph of y equals to x line will lie below the graph of 10x in the first quadrant. So that is the graph of y equals x line. Now these two graphs, they intersect in the third quadrant. So answer to this question will be C. So the smallest positive root of this equation will lie in pi to 3 pi by 2. So whenever we are solving problems related to sine, tan and x, we must remember this inequality. So if I'll draw the graph of sine x also, now sine x will lie below x. And that's how we'll draw the graph of sine, tan and y equals to x line. Thank you. Now the 19th graph is graph of factorizable polynomial functions. Now for polynomial functions, we actually draw the graph using curve tracing, but here we are not bothered about the exact graph. So here we just have to draw an approximate graph. So there are certain things which we can do in a polynomial function. Say for example, the function is given as x cubed minus 6x squared plus 11x minus 6. So if I'll factorize it, I'll get fx as x minus 1, x minus 2 and x minus 3. So that's my function fx. So I'll draw a number line. So I'll draw x-axis and y-axis. And I'll mark these roots. So the roots are 1, 2 and then 3. So I'll mark these 3 roots on a number line. So now in inequalities we know how to mark the intervals as plus, minus, plus. So sign of the rightmost is plus. So this is plus, minus, plus and minus. So that means my graph will be negative when x is less than 1. And it'll be positive between 1 and 2. It'll be negative between 2 and 3 and then positive again between 3 and infinite. So this graph will start from minus infinite. Then it'll pass through 1 and it'll take its maximum value. Then it'll pass through 2. It'll take its minimum value and then it'll go towards infinite. So that is the basic graph of this function. X minus 1, x minus 2, x minus 3. I'll take another example. Suppose I have to draw the graph of fx equals x minus 1, x minus 2 square and x minus 3. So again, I'll mark these points. So this is 1, this is 2 and this is 3. The sign of the rightmost is plus and then it'll be minus. Now at 2, because it's an even power, sign doesn't change, so it'll be negative and then it'll be plus. In this case, because it is plus, so this graph will start from plus infinite. It'll pass through 1. Now since it has a double root at 2, so it'll touch the x-axis at 2 and then again it'll be negative and then it'll pass through 3 and it'll go up to infinite. This is an approximate graph. So in this graph, we are not bothered about the details of these functions, like where it is going to take the minimum value and what's the minimum value. We just want the very basic shape of this graph. I'll take another example. Say for example, x square into x minus 1. So one of the root is 0 and the other root is 1. The rightmost is plus and then minus, and there'll be no sign change at 0. So this graph will start from minus infinite. It has a double root at 0, so it'll touch the x-axis at 0 and then it'll pass through 1 and then it'll go up to plus infinite. What if the question is fx equals x into x minus 1 whole square? Now here again, I'll mark 0 and 1. So this is plus, so there's no sign change at 1, so plus, and then at 0 will be minus. So this graph will start from minus infinite. Then it will become positive, and at 1 it has a double root, so it will touch the x-axis at 1 and then again it will go to plus infinite. So this is how we draw basic polynomial factorizable functions. So the 20th graph is graph of rational functions. So generally when we draw graph of rational functions, we use curve tracing. So for more detailed and accurate elaborate graph, we'll use curve tracing. Here we are just going to draw a very rough, very crude sketch of rational functions. So I'll take one example. Say for example, a function is given by fx equals x square minus 4 upon x square minus 4x. So first what I'll do is I'll factorize it. So I'll write fx as x plus 2, x minus 2, x and x minus 4. Now the roots of numerator are x equals plus or minus 2 and the roots of denominator are x equals 0 and 4. So I'll mark all the 4 points on x-axis. So I'll get minus 2, 0, plus 2, and then plus 4. Now because 0 and 4, they lie in the denominator, so my function will have asymptote at 0 and 4. So at 0 and 4, I'll draw vertical lines. So I'll draw dotted vertical lines at 0 and at 4. Now if you have studied limits also, if I'll take the limit x tends to plus or minus infinite fx, I'll get the value of this limit as 1. So this graph will also have a horizontal asymptote, and that will be at y equals to 1. So I'll draw a horizontal line at y equals to 1. Now I'll go back to inequalities. So what is the sign of the rightmost? So this is plus and plus. Sign of the rightmost is plus. So this is plus, this is minus, plus, minus, and plus. So now I'll start drawing the graph. So now in this case, there is horizontal asymptote here, and there is a root at minus 2, and there is a vertical asymptote at 0. So I'll draw this graph starting from 1, then it will pass through minus 2, and then it will have negative value, and then it will have an asymptote at 0. Now between 0 and 2, it has an asymptote at 0. It will be positive between 0 and 2, and then after 2, it will be negative, and then it will again have an asymptote at 4. Now between 4 and infinite, it has an asymptote at 4, and then it will have horizontal asymptote at infinite, so y equals to plus 1. So this is a very basic graph of rational function. And in the next class, we'll discuss how do we transform these basic graphs to create more complicated and stunning graphs. Thank you. The question is, we need to find number of solution of the equation x square minus 3x plus greatest integral function of x when the value of x lies between 0 and 3. Now there are two ways of solving this question. Now one method is, I'll take three separate intervals. Case 1, when the value of x lies between 0 and 1. So when x lies between 0 and 1, what you know is greatest integral function of x will be 0. So I'll put it 0. So I'll get x square minus 3x equals to 0. So I'll get the value of x as either 0 or I'll get the value of x as 3. Now 3 doesn't lie in this interval. So the only value that I'll choose from here is x equals to 0. Now second case, when the value of x lies between 1 and 2. So when value of x lies between 1 and 2, the value of greatest integral function is simply 1. So if I'll put this value, I'll get x square minus 3x plus 1 equals to 0. So the value of x I'll get is 3 plus minus under root of 9 minus 4 by 2. So there will be 3 plus minus under root 5 by 2. So the values of x will be either x is 3 minus under root 5 by 2 or x is 3 plus under root 5 by 2. Now root 5 is 2.2 something. So 3 minus 2.2 something will be 0.7 something. 0.7 something divided by 2, 0.35. So which is less than 1. So it doesn't lie in this interval. And 3 plus root 5 by 2. So there will be 5 divided by 2. So there will be greater than 5 point something should be greater than 2.5. So in this case, this also, it doesn't lie in this interval. So there will be no solution in this given interval. Now the third interval is when the value of x lies between 2 and 3. So in that case, the greatest function of x will be simply 2. So if I'll put it in the equation, I'll get it as x square minus 3x plus 2 equals to 0. So from here, I'll say the value of x is either 1 or the value of x is 2. Now 1, it doesn't lie in the solution. So I'll choose only one solution, and that is x equals to 2. And finally, when the value of x is 3, so when the value of x is 3, if I'll put it, I'll get what? 9 minus 9 plus 3 is equal to 0, which is 3 is equal to 0, which is not true. So the only solution possible in this case is either the value of x is 0 or the value of x is 2. So there are two solutions possible in this case. Now another way of solving the same question can be using graphs. So what I'll do is, I'll draw the two graphs I'll write it as greatest integer function of x, and this is 3x minus x square. So I'll draw the graph of greatest integer function of x, and I'll draw the graph of y equals 3x minus x square. So first I'll draw this graph. So it's a parabola opening downwards, a roots at 0 and 3. So its vertex is at 1, 2, and then 9 by 4, there'll be 2 point something. So that is the graph of y equals 3x minus x square. Now I'll draw the graph of greatest integer function of x. So this is 0. Between 1 and 2 it will be 1. And between 2 and 3 it will be simply 2. So at 3, this value will be simply 3. So these two graphs, they intersect at 2 points. And one of the point is x equal to 0 and the other point is x equals to 2. So there are two solutions to this equation. Here the question is, find the number of solutions of the equation sin x is equal to greatest integer function of x. Now we know that greatest integer function, it's an integer. So that means sin x should also be an integer. So now in this case, sin x can only have three integral values. Either the value of sin x, it can be -1, or the value of sin x, it can be 0, or the value of sin x, it can be +1. Now, when the value of sin x is 1, the value of x is minus pi by 2, which is minus 1.54. And if I take greatest integer function of x is also -1, then I know the value of x should lie between -1 and 0. Now, minus 1.54, it doesn't lie in this interval. So there is no simultaneous solution to this case. So I won't get any solution from this. Now for the second case, when sin x is 0, then x is simply n pi, and one of the value will be x equals to 0. Now if I'll take greatest integer function of x is also 0, so then the value of x should lie between 0 and 1. So here we have a simultaneous solution at x equal to 0. So from here, one of the value that I'll get is the value of x, it should be 0. Now the third case is when the value of sin x is 1. When sin x is 1, then x is pi by 2, which is 1.54. And here, greatest integer function of x, it should be 1. So that is the value of x should lie between 1 and 2. Now 1.54, it does lie in this interval. So another solution to this equation is when the value of x is pi by 2. So there are two solutions to this equation. So number of solutions of this equation is simply 2. Another way of solving the same equation can be using graphs. So I'll draw the graph of sin x. If I'll draw the greatest integer function, so it will be this one. Then it will be here. So these two graphs, they intersect at these 2 points. So one of the point is x equal to 0 and the other point is x equals to pi by 2. So from graph also we can say the number of solution to this equation is simply 2. Now question number 25, it says we need to find number of real solutions of the equation x square equals e to the power x. Now in this question we just need to find number of real solutions and not the solutions itself. So we can solve this question using graph. So we can draw the graph of exponential function and we can draw the graph of y equals x square. Now a common mistake that a student can make in this question is, so we generally draw this exponential function and then if we draw this x square, then they may say these two graphs, they intersect at 2 points. So number of solutions in this case is 2, which in this case is completely wrong. Now we know that exponential function increases rapidly as compared to x square. So if we have to draw the graph of x square, and suppose that's your graph of x square, and suppose this is the graph of exponential function. Now exponential function increases rapidly as compared to x square. So these two functions, e to the power x and x square, they'll never intersect when x is greater than 0. So they'll have only one point of intersection. So number of real solution of this equation will be only 1 and not 2. In this video, we'll discuss a very interesting and unique problem in differentiability. Now it says that we are given a function f which is an injective function, that is it is 1 1 in the domain a to b and range c to d. If alpha is the point in open interval ab such that f has left hand derivative L and right hand derivative R at this point x equals alpha, where both L and R are non-zero and they are different and they are negative, then we need to find left hand derivative and right hand derivative of its inverse function at x equals fa respectively. So there is a lot of information given for this question. Now we are given this function which is 1 1 and which is defined from a to b, and then it says it is not differentiable at alpha. Now its left hand derivative at alpha is L, which is negative, and its right hand derivative at alpha is R, which is also negative. Now say we have this point alpha. Now left hand limit at alpha is L, which is negative. So that means this function is decreasing in the left neighborhood of alpha. And right hand derivative is R, which also is negative but different. So on the right neighborhood of alpha also, this function will be decreasing but with different slope. Now we need to find left hand derivative and right hand derivative of f inverse at x equals f alpha. Now this function, it is defined in the domain a to b and its ranges from c to d. Now at alpha, if we draw this left hand derivative, its slope is L, and in the right neighborhood of alpha, this slope is R. Now we know that for inverse function, we just have to take reflection of this function about y equals x line. So if we draw this y equals x line, and if we take reflection of this function about y equals x line, then this function will be drawn like this, and this part will be drawn like that. So we have this point now. Now this is alpha and this is f alpha, because this point was alpha and f alpha, and for inverse function x and y, they interchange. So this point is alpha and f alpha. Now if we look at this left hand side tangent at alpha. Now suppose this is delta x, and here it is delta y. So we can write delta y upon delta x, it is equal to L. Now if we take the reflection of this tangent about y equals to x line, then it will be drawn like this. Now here delta x and delta y, they'll interchange. So in this case, whatever was delta y will now become delta y will become delta x. So in this case, slope of this tangent, it will be delta x upon delta y. And this delta x upon delta y is nothing but 1 by L. Here if we look at this graph,
then for this function fx, it was left-hand derivative. But for this inverse function f, it is on the right side of f alpha. So that means right-hand derivative of f inverse x at x equals f alpha, it will be 1 by L. Now in the same way, if this is R, and if we take its reflection, here it will be this 1 by R. So previously, which was right-hand derivative for fx, now translates to reciprocal of left-hand derivative of f inverse x. So left-hand derivative of f inverse x at x equals f alpha will be 1 by R. So answer to this question will be 1 by R and 1 by L. So previously for fx, left-hand derivative is L, but for f inverse, left-hand derivative is 1 by R, and for fx, right-hand derivative is R, whereas for inverse, its right-hand derivative is 1 by L. So that is the difference between the two functions. Now all this is very difficult to visualize in a graph. So what we'll do is, we'll try and solve this question analytically. Now we are given this function. So again, we'll draw the function. So we are given this function f, which is 1, 1, and at alpha, it is not differentiable. This point is f alpha. Left-hand derivative at alpha, it is L, and right-hand derivative at alpha, it is R. Now for this function, we clearly know that it is a decreasing function, which means f alpha minus h, it is greater than f alpha and will be greater than f alpha plus h. Now left-hand derivative at alpha, which is f dash alpha negative, it can be expressed as this limit h tends to 0, f alpha minus h minus f alpha upon minus h, it is L, and right-hand derivative at alpha will be this limit h tends to 0, f alpha plus h minus f alpha upon h, and this is equal to R. So this is already given in the question. Now what we'll do is, we will let beta equals f alpha. So this point, this is beta. Now if we increase beta, that is if we write beta plus h, then if we increase beta, which is say beta plus h, it is increasing the value. That means we are moving towards the left hand side of alpha. So that means this is equal to f alpha minus h dash, and if we are decreasing the value of beta, then beta minus h dash, we are moving towards right of alpha. So then will be this f and alpha plus some small value h dash. Now we'll start writing derivatives of its inverse function. So left-hand derivative of f inverse at beta, which is f alpha, will be this beta negative, and we'll write this as limit h tends to 0, f inverse beta minus h minus f inverse beta upon minus h. Now basically f inverse beta minus h is alpha plus h dash. So we can write this as alpha plus h dash minus f inverse beta is simply alpha minus alpha upon, and then this minus h. We can write this minus h as f alpha plus h dash minus beta. Now here alpha will cancel, and when h tends to 0, h dash also tends to 0. Now this is limit h dash tends to 0, h dash upon f alpha plus h dash minus beta, and beta is f alpha. Now we can also write this as limit h dash tends to 0, 1 upon f alpha plus h dash minus f alpha upon h dash. And basically this is nothing. This is right hand derivative of this function f in the neighborhood of alpha. So this is right derivative at alpha, and right derivative at alpha is 1 by r. So left hand derivative of this function at fa, it is 1 by r, and in the same way we can find its right hand derivative. Now we can write its right hand derivative as f inverse beta positive, and this is limit h tends to 0, will be this f inverse beta plus h minus f inverse beta upon h. Now f inverse beta plus h is alpha minus h dash. So it will be this limit. Now h dash tends to 0, and this is alpha minus h dash, and f inverse beta is alpha. And again we can write this h as f alpha minus h dash minus beta. F alpha minus h dash minus beta, and beta is f alpha. Now here alpha and alpha will cancel, so we can write this as this limit h dash tends to 0, and we'll rearrange this as f alpha minus h dash minus f alpha upon minus h dash, which is nothing but left hand derivative alpha, and which is 1 by l. So left hand derivative is 1 by r, and right hand derivative is 1 by l. So we have solved this question graphically as well as analytically.